Hey, this is our second video on really a section about differential equations about slope fields. So um, we have learned how to solve certain differential equations, certain ones that are appropriate in this class where we can just solve them by separation of variables. A slope field is a way to kind of visualize what the solutions look like. So remember, when we get the solutions, we have a plus c, so there's many different answers. So a slope field is going to kind of show a representation of all of those things, kind of shows the general shape. So we're going to actually kind of follow this process, and so that's on your paper, so you can read through that some more, but we're going to actually do it right now. So, and when we find our slope field, then we're going to go ahead and solve it by the methods that we did so that we can sort of see how it fits on this graph. So we just have a little grid, and basically what we're going to do is we're going to represent the slopes of the tangent lines at the points that are on this little bit of the graph. If you do this on the AP test, they usually don't have more than 9 points or so that you have to fill in. So it's not that big of a deal to fill in. It's more that you could maybe match one or something like that. So I'm going to use a red pen so that you can see it better, and we're going to just simply use this chart to fill in. And I think on your paper you don't have the y column, but you'll see why we don't need the y column necessarily here, because if you see, this is dy dx equals 2x. So basically what we're drawing is a little tiny piece of a tangent line, so like a representation of what the little bit of the tangent line would look like just right at that little point. So I can just plug numbers in. I don't usually use a table, but I'll use a table for a couple of examples so you get the idea. I usually just plug the numbers in and do the arithmetic. So if I'm going to pick x equals -2, which means that basically we're right here on this column, then if I plug in -2 for x, I'm going to get -4 for dy dx. Now the reason I don't really need y written is because notice there's no y in the problem. So no matter what y value I'm at, dy dx is going to equal -4. So all we do at every value on that whole column is we make little tiny segments that have slopes that look about like -4. So -4 would be fairly steep. So at all of these places, we're going to make slopes that look like -4, and we just make little segments. So we're just kind of representing that if there was a curve drawn there, that's like the little piece of the tangent line and what it would look like. So let's go ahead and go for x equals -1. And again, the y's, this is going to be true for all of the different y's, so I don't really need that column. So if x is -1, 2 times -1 is -2, so dy dx would be -2. So now when x is -1, well, not quite as steep as -4, but still steeper than what -1 would be. And then I just go through and make my little segments. Now let's try when x is 0. Well, when x is 0, you're going to get 0 for the slope, 2 times 0. So everywhere that x is 0, you're going to have little horizontal tangent lines. So you might even find this to be better to use like a colored pencil or something that you can see on your grids when you are answering your questions on your homework. And then let's plug in x equals 1. So you're going to get 2 times 1, which is 2. So everywhere that you have x is 1, you're going to make a slope of -2. Those were a little bit too steep. It's not quite as steep. So we want to make a slope of 2 there. And then we're going to plug in 2 because that's all that this graph covers. You could plug in, obviously these could be made more extensively. If I plug in 2, I get 4, because I'm again plugging in right there. 2 times 2 is 4, so that's a little steeper. That's a little too steep. So these are a little steeper. So they don't have to be perfect. They just need to be roughly the kind of the right direction. Well, if we actually go through and solve this really simple differential equation by the method that we just did, we would get the integral of dy is going to equal the integral of 2x dx, because we're just going to separate the variables. Integral of dy is y. Integral of 2x is x squared, and then plus a constant. So the solution to this differential equation is y equals x squared plus c. Well, if you look at this graph, you should be able to see how there would be a bunch of parabolas there, and that would totally make sense. That would be y equals x squared plus c. So this is a up and down, this is a parabola that goes, and the plus c simply moves it up and down. So you can kind of see the general sort of shape if you kind of look at the way the tangent lines are going there. Okay, so let's go to the next example. So this time we also have one that does not depend on y. We have 3x minus 2. So we're going to again plug in the range of x values that we have, which is -2 to 2. So if I plug in -2, I get 3 times -2 is -6 minus 2. So dy dx is -8. So now when x is -2, and again, all the y's will all give me the same thing. So I could look at -2, -2. My slope is going to be -8. That's almost straight up and down. But if I do -2, 1, still going to get a slope of 8. All of these are going to give me a slope of 8. So it doesn't matter what y is. If I plug in -1, I do the same thing. 3 times -1, -3 minus 2, -5. So still really steep, but just not quite as steep as the other one. So the best that you can. And that's what you get all the way down. If we have x equals 0, we're going to get -2. So again, just not quite as steep. And then if x is 1, we're going to get 1, because we'll have 3 times 1 is 3 minus 2 is 1. So now we go the other direction, and 1 is exactly right through the diagonal. Since these have little squares, that's actually pretty easy. So there's going to be your slope of 1, and then you plug in 2, you're going to get 6 minus 2, which is 4. So now you're going to have a steeper one going right through there. And so there's again another example of a slope field. So I'm not going to solve that one, but you're going to get, you can kind of visualize, I hope, the kind of going through there. We'll look at one on the next examples, a couple of examples later that has more of the tangent lines in there, so it's a little bit easier to see that. Okay, so here's another one. Now this time we do have x and y, but I'm not going to fill in the whole entire table. I'm going to do a lot of this kind of in my head to fill this in. So basically you're just doing a bunch of arithmetic. So I'm going to start with -2, 2. So that's the point on the upper left. So if I plug in -2 for x and 2 for y, that'll give me my dy dx. So 2 times -2 is -4, plus 2 is going to give me -2. So go over to the point -2, 2, and make a slope that looks about like -2. And then I would just keep doing that. So this time I can't just do them all the way down because now y does matter. So now if I look at -2, I have to consider, like say the point -2, 1. So if I'm looking at -2, 1, again, I still just plug in. So I plug in -2 for x. That's going to give me -4. I plug in 1 for y. So -4 plus 1 is going to give me -3. So then I'm going to put at -2, 1, I'm going to put -3, so a little bit steeper than the one above it. If I go to -2, 0, I'm going to get oh, I just realized this isn't even the same as your example that you have maybe on your paper. So I guess just watch on this one, and so we can look through it and see what it looks like. So when we plug these in, so we're just going to fill this one in, and you can just use this as an extra example. So if you do -2, 0, you're going to get -4 plus 0, which is -4. So at -2, 0, it's a little bit steeper. So imagine -2, -1, that's going to be -5. Then you're going to have -6. So this time they're all a little bit different, and it's really hard to distinguish that. But then I can just go plug in values and not have to make a table if I don't want to. I can just keep plugging in to 2x plus y. So if I'm at negative 2, 2, or negative 1, 2 this time, I'm going to have negative 2 plus 2, which is going to be 0. So I'm going to have actually a 0 slope there. If I go to negative 1, 1, I'm going to have negative 2 plus 1, which is negative 1. And then if I go to negative 1, 0, I'll have negative 2 plus 0, which is negative 2. And if I do negative 2, negative 1, I'll have negative 3. You can kind of see the trend on this, and they just keep getting steeper. And then I would just continue like that. So I guess since this is different than the example you have, I'm going to go ahead and just and kind of go through the points really fast here, and then we're not going to solve this one actually. So if I plug in 0, 2, for example, so 0 for x, 2 for y, I'm going to get 2. So now I have a positive slope of 2. If I do 0, 1, I'm going to get 1. If I do 0, 0, I'm going to get 0. And if I do 0, negative 1, I'll get negative 1. And then I'll get negative 2. And then you would just keep continuing like that. So 1, 2 is going to give me 2 plus 2 is 4. And then 1, 1 will give me 2 plus 1, which is 3. 1, 0 will give me 2. Then I'm going to get 1. Then I'm going to get, if I'm at 1, negative 2, I'm going to get 0. And then I could continue at the end. I'm actually going to stop there and stop with that. But I do want to notice something, because this is kind of important, because later you're going to have to try to match slope fields to other solutions. So notice that when you kind of go on that line there, you're getting that to end up having slopes of zeros. That's often the best way to sort of pick what thing might actually match together. Okay, so let's go and see if your next example is the same. That would be nice. So I think the next example is where we're going to try to distinguish and see if we can match. So one thing that you definitely want to look for is places where the slopes are zero. So where dy dx equals 0 is a huge one. That's kind of where I usually start. Then you kind of look at the slopes on the x and the y-axis and so on, and kind of find out if like all of the columns are all the same. They're all vertical translations. That was like the first couple of examples. They only had x in it. So everything vertically all had the same thing. The same thing would be true if only y was in the solution, the dy dx. So then they would all be horizontally the same. And then you're kind of looking to see where positive and negative to kind of help you match that. So for these examples, we have where we're supposed to be matching these. So you'll have to look on your paper to kind of see them all at once. But let's just go through each one to kind of figure out what it might match to above. So we're going to just start with A. So if we look at A, the very first place that I would look, now it kind of visualize here what you think the solutions are going to look like. I'm going to erase this, but you can follow. Do you see how a curve kind of goes like this? And you can kind of see what some of the families of solutions are looking like, because you can sort of see them fitting those tangent lines. On this side, they're going this way, and they get a little steeper, and so on. And here, you've got things going like that. So you've got families of solutions, and that's where that plus C changes things for us, okay? So what we're going to look at now, though, is we're going to kind of, well, I'm just trying to match up this dy dx. So I very often look at things like this. I notice that right here, along where it's 1, 1, 2, 2, 3, 3, 4, 4, and stuff, it appears that we have a slope of 1, which would mean, looking at the 4 different things we have. We have y over x over y, negative y over x, negative x over y. Well, if when you're at 1, 1, 2, 2, 3, 3, and so on, you have a slope of 1, then it's got to be x over y or y over x. So it's either number 1 or number 2 that fits this. So then I need to look at some other things. Well, let's notice that also, if you look here on the y-axis, you notice that you have a slope of 0. So when you have x equals 0, you're getting a slope of 0. So therefore, and if you look this direction, you'll see that you don't have any tangent lines, so they're undefined, which means that y must be on the bottom. That's causing you to be undefined when y is on the bottom. So therefore, this one right here, number 2, matches A. And you can sort of check if you just pick a few points and kind of look and see, does that seem like the right kind of slope? If you look at, you know, like the point, again, 1, 1, let's look at 2, 1. So like right here. Well, that slope appears to be 2. So if x is 2 and y is 1, 2 over 1, that's 2. So that kind of makes sense. So you can try more things. Okay, so let's look at B. So again, on B, I would notice I have the same thing. Right down here, I've got x equaling y, and I've got a slope of 1. This time, I don't have anything on, well, I can also notice that also this way I have a slope of negative 1. You know, so there's a couple of things that you can notice. And then, well, so our choice is either x over y or y over x. Well, we've already done x over y, so it must be y over x. So we can kind of look and see if that makes sense. So think about going over to points that are further out, like over here. If you look at this point, so that's, say, 3, 1. Well, you plug in 3 for x and 1 for y. If you have y over x and you plug in 3 for x and 1 for y, you get 1/3. Well, this is definitely a very flat line that probably has a slope of 1/3. And so we kind of look through that and we match that up. And so we would say this one is B. All right, so then let's look at C and D. So on C and D, the difference that you have is when you have those points where you have y equals x, now I've got a slope of negative 1. So that's the reason it fits the other two cases. I have negative y over x or negative x over y. Then you can kind of look again at some of the things, you know, like again, way out here, like if I'm looking at the slopes around the point 3, 1, they're super tall, which means that it must be 3 over 1, not 1 over 3 and negative, because the slope is steep, not flat, which means that this is x and this is y. So that's a way to look at it. So it must be negative x over y. You can try a bunch of other points. You can look at different things, but I would say that C must be this one. And then that leaves the last one to be obviously the last answer there, but let's kind of go ahead and look. And so right here again, when you have y and x are equal, like the points 1, 1, 2, 2, 1.5, 1.5, you get a slope of negative 1. So there's your negative y over x. When you get way out here, you're getting really flat, which is a really small number, like a small fraction. So that means x must be on the bottom to give you that, which fits number 3. So there's the kind of some of the kinds of things that you do when you're trying to match graphs up. Okay, so let's look and make sure this example is the same as what's written. So this one is the same. Good. All right, so this time we have a slope field that's given, and notice this slope field has a lot more points on it. So you should really be able to see, if you look at it, you can kind of see the basic shapes of the curves that would all be there. So what we're going to do is we're going to actually solve this differential equation, and then we're going to actually find the particular solution and graph it the best we can through the point 0, 1. So to solve this, we're going to have dy equals 1 over x plus 2 dx, and then we're going to integrate both sides. I'll go back to a black marker. So we integrate dy, we get y. We integrate the right-hand side. Remember, we're going to get ln of the absolute value of x plus 2 plus c. And now we want to find the solution for when we have 0, 1. So when x is 0, we expect y to equal 1. So we have ln of 0 plus 2 plus c equals 1. So therefore, c is going to equal 1 minus the ln of 2. And that's just what we end up with the constant. Sometimes we don't get the greatest thing. So we go back to this, we get y equals ln absolute value of x plus 2 plus 1 minus ln of 2. So this is the particular solution. And then we're going to go over to this graph and we're going to graph it. Well, I don't have any idea what that looks like, but it doesn't matter. I'm just going to go to the point 0, 1 and put a dot because I want the solution that goes through that point. Well, if I look at this graph, you should be able to sort of see, and you don't have to go through any of the points, you just have to sort of aim it the way that you can kind of see it aiming. So you can see here you're starting to get really steep tangent lines. So that would be an example of something like what your solution would look like. So you can kind of see, if you were to draw little tangent lines right on that graph, what that would look like. All right, so the last thing is really just what we've already kind of talked about, and that's integrating it, plugging in C, and so on. So we've really already done this. So I'm not going to do these 2 examples. You can certainly ask to see these notes in class, but we did the solution first where we solved all of these and plugged that in. So it's the same process that we just used for this one. You just solve it, get the plus C, take the particular condition that you have, plug it in, find C, get your answer. So that's how we get an exact solution. So that is it for slope fields. Your biggest thing you need to be able to do is draw little tiny tangent lines and do arithmetic. And don't believe that that is a small thing, because that's actually probably one of the most missed things that I have on any test. So work hard and do the problems on your homework well.